Hi everyone, I'm John Baker from the Met Office. Sorry I can't join you in person, but I'm looking forward to some AMOC sciencing. And this is a cartoon of the ocean's overturning circulation from Broca, showing the deep waters of the AMOC forming in the North Atlantic that upwell diffusively in the ocean's other basins. And more recently, westerly winds over the Southern Ocean have also been found to upwell these deep waters, with much debate since over the relative importance of these upwelling pathways. And we expect the AMOC to weaken this century, but there's a large spread in the amount of weakening in the latest CMIP6 model into comparison project. Here I'll show work we've been doing looking at the upwelling pathways of the AMOC in the CMIP6 ensemble. The main questions we want to answer are what are the historical overturning pathways in CMIP6 models and how do they change in a warmer climate? How do these pathways affect future AMOC weakening and what mechanisms are responsible for these dependencies? And can we use estimates of the real-world overturning pathways to constrain future AMOC weakening? This is a sketch of the pathways, which are the time means only integrated transports inferred from the overturning stream function. The Atlantic is at the bottom, the Indo-Pacific at the top, with the Southern Ocean Channel connecting the basins. And the AMOC either upwells in the Atlantic, called the Atlantic diffusive pathway, shown by the grey box, or it flows into the Southern Ocean, which we define as latitude south of 34 south. And some of the waters flown into the Southern Ocean ultimately upwell in the Southern Ocean upper cell, shown by the yellow and the pink boxes, that together give the total Southern Ocean wind pathway, shown by the orange box. And then the remaining deep waters of the AMOC flow into the Indo-Pacific, where they upwell diffusively and then return to the Atlantic by the Southern Ocean zonal currents. And this is the green box, which we call the Indo-Pacific diffusive pathway. So we have three main upwelling pathways of the AMOC, the Atlantic and Indo-Pacific diffusive pathways, and the total Southern Ocean wind pathway, which together give the strength of the AMOC. And these pathways define the upwelling routes of the AMOC that are required to satisfy incompressibility in the ocean. To separate these pathways, we use the overturning stream function shown here in the Atlantic on the left, the Indo-Pacific on the right, and globally averaged in the Southern Ocean of each plot. In the Atlantic, the AMOC is shown by the positive red shaded stream function, which represents a clockwise circulation, whereas the Indo-Pacific has an anti-clockwise circulation. And the Atlantic diffusive pathway is calculated from the volume of the AMOC with closed streamlines in the Atlantic. The total Southern Ocean wind pathway is approximately equal to the strength of the Southern Ocean upper cell at 34 south, and we then calculate the Indo-Pacific diffusive pathway as a residual of the AMOC strength and the two other pathways by rearranging the equation at the top to get the green box. And our method is based on continuity of volume in the ocean. On to the results. These are the magnitudes of the three upwelling pathways against the maximum AMOC strength in each CMIP model, averaged over the historical simulation. There's a large spread in the AMOC strength and the pathways across the ensemble. The Atlantic diffusive pathway on the left and the Indo-Pacific diffusive pathway on the right are positively correlated with the AMOC, but the total Southern Ocean wind pathway in the middle is negatively correlated with the AMOC. Here we plot the historical AMOC strength against its change by the end of the century in each of the SSP or shared socio-economic pathways. The weakening of the AMOC is dependent on its historical strength, as found in previous studies, so models with stronger historical AMOCs weaken the most by the end of the century, with the strongest relationship in SSP585 on the right, which is the high-end warming scenario. This is the same plot, but now with each of the historical upwelling pathways against AMOC weakening, and there's a much stronger correlation with the Indo-Pacific diffusive pathway on the right, which explains 81% of the variance in future AMOC weakening, compared to the 55% explained by the historical AMOC strength in SSP585. And the other pathways have weaker relationships with AMOC weakening. This shows the change in the pathways over the 21st century. At the top is the change in the absolute magnitudes, and at the bottom are the changes relative to the historical period. From left to right is the AMOC, the Atlantic diffusive pathway, total southern ocean wind pathway, and the Indo-Pacific diffusive pathway. The AMOC on the left decreases in all of the models. The Atlantic and Indo-Pacific diffusive pathways also decrease, whereas the total southern ocean wind pathway is fairly stable. And models with larger historical Indo-Pacific diffusive pathways have larger decreases in this pathway, which decreases to 0 in most models by the end of the century. And the historical magnitude of this pathway acts as an upper limit on its decline, so it modulates the AMOC weakening. And this pathway decreases partly due to the Indo-Pacific overturning weakening, and partly because the cell overlap between the AMOC and the Southern Ocean lower cell is reduced as the AMOC shoals. But regardless of the mechanisms, we find this pathway is a strong constraint on AMOC weakening. So we estimate this pathway using observation-based estimates of the real-world overturning, and we use 3 global ocean reanalyses that assimilate observations into an ocean model. These are GLORAN, ECHO, and a robust diagnostic simulation, and we also use the inverse model estimate of Lumpkin and Spear. And using this plot shown earlier, we can match the Indo-Pacific diffusive pathway from each estimate to the x-axis, go up to the line of best fit and read off the AMOC weakening. And the shading here shows the 95% prediction intervals, which gives us the uncertainty. This shows the observation-based estimates with the Indo-Pacific diffusive pathway circled, and there's a wide range with almost no pathway in ECHO or the inverse model, whereas it's quite large in GLORAN and the robust diagnostic simulation. So based on these, the emergent constraint relationship suggests an AMOC weakening by the end of the century of 29 to 61% under SSP 585. And although there's large uncertainty, the relationship is strong. So if we can reduce uncertainty in this pathway, we could greatly constrain the future AMOC weakening. So what next? Reducing uncertainty among ocean reanalyses would narrow the pathway estimates, but direct measurements from an Indo-Pacific array would be most reliable. Of course, there are many obstacles, but I think this would be a big gain for understanding and predicting changes in ocean circulation. And why there's a wide range in the model overturning pathways is also an important question to answer. To conclude, models with larger historical Indo-Pacific diffusive pathways have greater AMOC weakening with a strong relationship found, and if we can reduce uncertainty in this pathway in the real world, we could greatly constrain AMOC weakening. Our study has been published in GRL, so please check this out for further details, and thanks for listening.